All right, so let's talk about aerodynamics. First, we got to figure out why a plane actually flies. So if we think about an airplane, we know that gravity is always pulling you down. So we always have gravity wanting to pull you to the earth. So to overcome that, we have to have an opposite force going up, which is what we call lift. So basically, if the lift is equal to gravity or is greater than gravity, you're going to be flying. So let's talk about lift. How lift works on an airplane wing is Bernoulli's principle. He basically says as a fluid moves faster, it has less pressure. So if you think about a pipe, you have a pipe. The pipe gets narrow in the middle and then gets big again. In that middle section, that fluid is going to be going a lot faster. And as it gets faster, it creates less pressure. And that is how an airplane flies. It creates less pressure above the wing as it does below the wing. Which how it does that, you have the wind hitting the wing. The distance traveled over top is a whole lot longer, so the air has to go quicker over this longer surface area. So it goes quicker over top, slower over the bottom. So according to Bernoulli's principle, the faster fluid is going to have a lower pressure, which in this case is on the top. So you have low pressure on the top of the wing, high pressure on the bottom of the wing, which high pressure always wants to go to low pressure. You get a lifting action, which makes your wing generate lift. So that is actually how a wing flies. But we can change the amount of lift we make by changing the angle of attack on the wing. So we have a couple parts of the wing here. We have the chord line, which is a line from the midpoint to the end of the wing, and it's kind of like the angle of your wing. And then you have the relative wind, which is the air or the fluid hitting the wing. So if you change the chord line here, you increase it. The angle between the chord line and the relative wind is your angle of attack. So as you increase this angle, you actually generate more lift. And I hope this isn't flipped on your screen, but for me, we have angle of attack increasing with this direction, lift increasing with that direction. And so as you increase the angle of attack, you're getting more lift. And then at the very top, you have the critical angle of attack, which is the most amount of lift you can get out of that wing. And then at that point, it will stall if you increase the angle of attack anymore. And that's simply because if you increase this wing, if you get the angle of attack too steep, it is going to disrupt the airflow. You're no longer going to have laminar flow over the wing, and you basically, it doesn't act as a wing anymore, and you fall out of the sky. So that is how angle of attack correlates with lift. There's also an equation, but we won't cover that. So we have that. And now let's talk about stability and controllability in an airplane. So I have my little airplane here. Imagine we're flying along. We're just flying, and I pull back on the yoke, and I just let go. What's going to happen? Are we just going to climb forever? Are we going to climb and go down? What's going to happen to our airplane? Well, we have a few different types of stability. Let me clear up my board here. You basically have dynamic stability and static stability. Those are the two types of stability you have. In static stability, that's the stability of it wanting to return as soon as that input happens. So say we're flying along and I pull back on the yoke and let go. Static stability, so I let go here. Static stability, it wants to return back to where I was at. So that would be considered positive static stability. Then you have neutral static stability, where same thing, but instead I pull back on the yoke, I let go. But instead of it returning, it continues on the course that let's see if you can see that better there. It continues on the course that I let go. So that would be neutral static stability. And then you have negative static stability, which I pull back on the yoke, I let go. It actually increases and does one of those. And that would be a very bad airplane. You would not want that type of stability in your airplane because it would be unflyable. So that's static stability, it wanting to return right back to the point. Now dynamic stability, let's look at this, our flight path here. So let's say we have positive static stability in our airplane. If we had positive dynamic stability, that means as we come through here, now we're descending, it's going to want to go through our altitude that we were at. So say that's our altitude we were at. It's going to want to go through that. What dynamic stability is it wanting to come back to the altitude we were at. So it would come back here, maybe go here, and then it's going to come right back to where we were at. So if this this oscillation, if it gets smaller and comes back to, say we're at 5,000 feet, we do that. We climb up, we go back down, go through our altitude, come back up, come back down. If it starts getting lesser and lesser and holding out that altitude we did that at, then that would be positive dynamic stability. Then also if you have neutral dynamic stability, it'd be the same thing, but instead of it getting narrower, you just have this oscillation all the way down, and then negative dynamic stability, it would get a whole lot bigger as you over time. So most airplanes, at least the ones we're flying in, are going to have both positive dynamic and positive static stability, and that just creates a better flight experience, makes it easier to fly. If the wind hits you, you bump up and then you go down. It's going to hold the altitude. So most airplanes, you want to have this kind of stability. All right, let's talk about that. So how does a plane actually turn? So you have flight controls, obviously, on your airplane. That would stay still. So let's talk about how a plane behaves in a turn. So bear with me here while I make some space. Let's say we have this airplane. We're looking at it from the back. Let's say we're looking at this airplane. We're from the back here. We have this lift going up. That's our lift. We have gravity pulling us down. Okay? As you get into a turn, say our airplane is now like this, that lift is now not completely vertical. So you have lift going up and you have lift going sideways, and that is actually how our airplane turns. As you roll, that vertical component of lift starts going sideways, and it pulls us into the turn. And so now let's think about this. We now have less vertical lift because it's trigonometry. But you have the lift going this way now. It'd actually be the other way. You'd have the vertical components here, the horizontal components here. So the lift you're generating up is less than the total lift. Altogether, the vertical lift's less than the total lift, horizontal lift's less than the total lift. But that means we've lost some of our vertical lift when we're in that turn. So if you just were to roll the airplane and hold and not do anything, you would descend, because that vertical lift that was used to be going up is now going sideways. You don't have as much. So you'd start descending. So how do we counteract that? Pull back on the yoke a little bit. That makes our elevators pitch down, which lifts the nose, increases the angle of attack, gives us more lift, and then we'll maintain altitude and go through the turn. I'm about to sneeze. All right, sorry about that. Let's talk about torque now. So you have this big propeller on the front of your airplane. Propeller spins counterclockwise here. So as the propeller spins, it's pushing against the airplane. So I'm trying to figure out what angle you guys are looking at. So the propeller is going to spin this way. that's going to twist the airplane to the left. And this is where we get some of our left turning tendencies. We have 4 of them, which I'll go over. So you can think about this as like, imagine you're sitting in a swivel chair and you have a table and you push against the table. Even I'm pushing that way, so my body turns this way. So it looked something like that. So that's how torque works. And that creates a left turn. Our plane wants to go to the left as that propeller spins faster. We also have the spiraling slipstream, which is where as the propellers spin, it creates a slipstream, and it spirals around the aircraft, and it hits as it goes around the aircraft, it hits the rudder on this left side, and it turns the airplane to the left. So that's actually one of our other left turning tendencies. So you can think about it as the wind, the prop wash going around the airplane and hitting the rudder, which turns the airplane. Then also have P factor, which if you look at the pitch of a blade on about break my airplane. If you look at the pitch of the blade on a prop, if you ever go out there and look at one, you'll see that it kind of acts like a wing. So essentially, as you pitch up, with the direction of the wind, this side, the right side of the prop, is now having a greater angle of attack than the left side. These are the angles of the blade, which means the right side is getting a better bite and is creating more thrust. And so it wants to pull the airplane to the left. That's why when you do power on stalls, you have to give it extra right rudder. And then finally, the most confusing one is gyroscopic precession. And I'm going to read this from the book because it is very confusing, and I myself do not know the full reason of why it happens. So anytime a force is applied to deflect the propeller out of its plane of rotation, the resulting force is 90 degrees ahead of and in the direction of the rotation and in the direction of application. That was a lot. So let's think of our airplane here. When you apply a force, so say we apply a force up on the airplane. Gyroscopic precession means that we will have an extra force 90 degrees ahead with the rotation and in that direction. So if we push up, the prop spinning this way, 90 degrees of that rotation puts you on the left side of the airplane. The resulting force would be to the left. And that is what creates another left turning tendency. So gyroscopic precession is very confusing. That's all you really need to know is that it's 90 degrees in the direction of rotation creates your resultant force. Okay, so load factor. So I'm going to also read this straight from the book. It's in chapter 5, page 33. So the load factor is measured, you can think about this as the G's of how many G's you're pulling. And it's the unit of force equal to the force exerted by gravity on body at rest. Wait. Okay, here we go. In aerodynamics, the maximum load factor at any given bank angle is proportion between lift and weight and has a trigonometric relationship. The load factor is measured in G's, a unit of force equal to the force exerted by gravity on a body at rest, and indicates the force to which the body is subjected when it is accelerated. All right, so let's think about this. So as you go into a turn, you're going this way now. You pull back, you're maintaining that. You're going to have a positive load factor on the airplane, which is a force pushing down. That's why when you go into a turn, you feel that force into your seat. And it's measured in G's. So a load factor of 2 G's would be everything weighs 2 times as much as gravity, because gravity is 1 G. So 2 G's would be 2 times as much as your weight. And so we have to think about this in airplane design, because as you go into that turn, you're experiencing a great load factor. The more you bank, the greater load factor it is. It's in my mind, it's the best to think about this is you watch Top Gun, they pull, they feel those G's. That's load factor. So in our airplanes, I believe it's a 3.8 G is our max load factor we're allowed to use. And that's basically saying anything greater than 3.8 G's, you're risking to break the airplane. And so if you think about that, imagine the wings have to support the weight of the airplane. If you go to 4 G's, the airplane weighs 4 times as much as what it does on the ground. So if it's 2,000 pounds, 4 G's, it makes it an 8,000 pound airplane. The wings can't support that weight and they'll snap off. More than likely your stabilator is what will actually snap off. But so that's the importance of load factor. So if I actually ask you in front of me, I'll ask them this. So if our baggage compartment says it's a max weight of 100 pounds, and our airplane is rated for 4 G's. Sorry, if our airplane is rated for 4 G's, a load factor of 4 G's, and our baggage compartment says a max of 100 pounds, does that mean if we put 50 pounds of weight in there, or let's say 100 pounds, if we put 100 pounds of weight in our baggage compartment and it's rated for 4 G's, if we pull 4 G's, that bag is going to weigh 400 pounds. Would that be exceeding the limit of the airplane? I'd let them answer that. Then I'll explain to them. It's actually not going to exceed the limit of the airplane because the airplane was designed with that in mind. So that 100 pound weight limit in the baggage compartment is actually rated for 400 pounds because of the, it takes load factor into account of that. So that's how load factor works. There's also some things where load factor is going to affect your stall speed, affect some other things, but we will not get into that today. Finally, the last thing we'll talk about is wingtip vortices. So we have our wing, it generates lift. We know that. It has lower pressure on top, higher pressure on bottom. Air always wants to go from high to low. Everything wants to go from high to low. So the high pressure on bottom, it wraps up and around to the top, if you can kind of see that. So the high pressure on bottom wraps up around the top, and that creates a slipstream, a spiraling slipstream behind the airplane. It'd be best to show you a picture of it. I'll pull up a picture real quick. Here's a good one. Oh, this might be a little weird, but okay. So you can see that spiraling effect behind the wing. That's called wake turbulence, and that's caused by the spiraling slipstream of the wing. A couple ways we need to be careful of that when we fly, because a heavy airplane in front of us, it puts out quite a bit of wake turbulence there, and that can easily, in our small airplanes, flip us and put us in a bad situation. So if an airplane's taking off in front of you, a big airplane, and you're holding short, they take off, they climb out. The greatest amount of wake turbulence they're going to make is right there at rotation as they climb out. So we want to make sure we rotate before them and climb out up above them, because wake turbulence goes down and out. So we have to think about that. So we want to get off the ground before them so we don't have to worry about their wake turbulence. As well, if a plane's landing in front of you, you watch where they land. You want to land after them, because remember how I said wake turbulence goes down and out. So if you land out after them, that wake turbulence can't affect your airplane. You also need to consider the wind, since wake turbulence goes down and out. If you have a pretty good wind from the left here, it's going to hold that onto the, could blow that over to a parallel runway. So if you're on that runway and you have a really strong wind blowing the wake turbulence to you, that could affect you as well. And so that's my lesson. It's It's probably a little rough, but you know. I'd ask you, have any questions? And I covered everything in my lesson plan. Yeah. So have a good day.